And then let me share my screen. Okay, can you guys see my screen?
Yeah.
Okay, that's great. All right, welcome guys to another, learning session where we learn zero-knowledge proof together. So today, we talk about this, topic we mentioned briefly touched about since the first one called trusted setup. I think this is a term that's being thrown around, and so we are going to look into it and see, what it is, why is this an issue, and what are some ways to hopefully to, if not to completely remove it, and how to alleviate the risk. Okay, so let's get into it. So for people who have been into the, previous two sessions, so we talk about, ZK snarks. Basically it's one of the most popular type of zero-knowledge proof protocol out there. Okay, we have one more guy joining. Hey, Zach. Hello. Okay, yeah, maybe later on. Anyway, we have one more people joining. Hey, Zach, we just got started. Welcome here.
Thank you. Sorry I'm late.
No problem. Is the hurricane good in your place?
Yeah, I'm lucky to be on the east coast of Florida, so we didn't get it so bad.
Okay.
Feel bad for the other side, but I'm fine. Thank you.
Okay, no problem. Okay. All right. So we are talking about trusted setup. So for people who have not into our previous sessions, so when you're using ZK Snark, the first step is a setup phase. Basically you want to prove a function or computation, which is F here, and you go through this. G is like a generator function of the ZK Snark, and then it outputs a pair of keys. One is a prover key, one is a verification key, of course, by the name, right? So when you are producing the proof by the prover, you need the proving key, and then when the verifier verifies the proof, you need a verification key. But also there's a slide, that's a, which I put in the little square here. This, this little parameter usually denoted as lambda. So this is where the fun comes from. Basically, this is like you can think about it like a random number generator. It generates some randomness, and then this has to be input into the generator as well. So together they produce the pair of keys I just mentioned. So in the literature, this one is usually called the so-called toxic waste. And I'm going to talk why it's called like a toxic. So you can think about, this is, as I talked before, the zero knowledge, you can say, hey, the prover can prove to the verifier, something, but it does not tell, the secret to the verifier itself. So how does he do that? So he runs through this zero knowledge protocol. He can convince the verifier without telling him the secret. But here, that's a trick, like a backdoor. The only exceptions is, typically when the verifier can produce when the prover can produce a proof, which the verifier accept, that means the prover knows some secret, which usually we call the witness. But that's one exception, only one exception here. So basically, if somehow the prover knows this lambda, basically it's called toxic waste. That's why it's called toxic, right? Because if somehow the prover gets access to this secret number, lambda, he can produce a valid proof. The verifier will accept, but he doesn't actually know the witness. So for example, right, give simple example, maybe he say, hey, Alice want to prove to Bob, hey, I know some solution to this Sudoku problem. So usually when you run this setup, it's usually by some trusted third party, and then he run through this using the ZK Snark proof, and he can produce a proof. If Bob check the proof is good, he's sure that Alice actually knows the solution. But here's the trick. If Alice somehow get access to know the lambda, even he doesn't know the solution, he can still produce a valid proof. So we don't want that to happen. So that's why it's absolutely critical, in the setup phase, after this setup is finished, you get the pair of keys. Whoever performs the trusted setup has to throw this away. Otherwise, it's going to be toxic, meaning, you can generate invalid proof, actually. Does this make sense?
Yes.
So the question here is, the question here is, the question here is, if you have this secret number you want to throw away, how did you make sure nobody knows this? Because the whole thing is to make sure, Alice doesn't trust Bob, right? So if you have to introduce some trust third party, that's pretty much invalidate the whole thing, right? Because if you already trust somebody, why not just Alice tell the secret, to the trust third party, and the trust third party just tell Bob, hey, it's good, trust me. You see the issue is a kind of dilemma. On the one hand, the whole purpose you are using this zero knowledge proof is, Alice doesn't trust Bob. And then in order to go through this problem, Alice and Bob both has to trust third party, which is, it's not desirable, to say the least. And if you talk about, a lot of applications, people are using this to design kind of like a private or even anonymous, currencies, so-called cryptocurrencies, right? So if you, for example, Zcash, right? This is one of the prime examples using zk-SNARK. So if you know this set of parameter at the beginning, you can actually produce proof you own like trillions of even gazillions of Zcash without actually owning any. So this is very dangerous. That's why it's called toxic waste. It's coming from the term as if you have a nuclear reactor, right? So you have, once you get it running, you can producing the waste, and the waste is, because of radioactive, so it's kind of toxic. So the same thing here is very dangerous. So for anybody who has this knowledge, he pretty much has a superpower. He can produce, he can fake proofs. Is this issue clear right now? Okay. Okay, that's good. Let's keep going. So we just talked about, hopefully I just convince you why this, this trust setup is an issue. Because if somebody gets to know the toxic waste, he can pretty much, invert the whole proof process. You cannot trust it anymore. So what are the number of ways to address this issue? So in reality, we have two ways, pretty much. One is the so-called secure multi-party computation. This is some kind of like a cryptography. So just somebody raise a hand. Anybody has heard about this term before? MPC? Secure multi-party computation? Okay. Yeah, so, if you are in a Bitcoin space, that's definitely one. If you have ever used, let's say, Handcash, right? So you probably heard about this threshold signature. So that's one very prominent example of MPC. So that's just a specific example. So what does it mean in general? So basically, let's say you have more than one parties, right? And each one of them has some secret. Let's say here, 3 parties. They know X, Y, and Z, and they want to compute some joint function. Let's say they want to compute, let's say, sum, right? Or they want to compute, product or whatever, of this. Let's say they want to produce F, X, Y, Z, that's equal to the sum of X plus Y plus Z. But here's a trick. So usually you can just give to some trust third party and they put together and they compute it, right? So the trick here is they want to do this without sharing the input with anybody else. So they want to, you see this lock here? So pretty much they want to, everybody keep the private input private, but they can still perform some protocol like a magic. Pretty much just cryptography, so they make sure they can compute the right function even though they do not share the input with each other. Does this make sense so far?
Yeah, that's exactly how Handcache works.
Yes, yes, that's just a very good example. I think the canonical example is, this is so-called, I don't know, they call it Yaw's millionaire problem. So basically, it's a fun example. Just two millionaires. I mean, when the NPC is divided, so millionaire is still huge. It's still huge. So today we can call it the Yaw's billionaire problem, probably. So basically, two billionaires, they go to a dinner together, and at the end, they want to say, hey, whoever has a higher net worth is going to pay the bill, okay, for whatever reason. But here's the thing, right? So they may not want to tell each other, hey, what is your net worth? Maybe I'm 3.5 billion, you are 4.6, whatever. The key issue, they don't want to tell each other, but they still want to have a guaranteed way to definitively prove which one have a higher net worth. So how do they do it? I think that's a huge, you can Google this Yaw's millionaire problem, but it's kind of like advanced cryptography. We're not going to cover it today. It involves all kind of like a heavy math, like Gabor circuits or whatnot. So basically, for now, for us, we don't have to worry about that. Basically, you can treat this. There's existing ways to do MPC, so which lets you to compute some joint function without disclosing all the inputs. So that's what people have been trying. So what's the basic idea? Let's say you want to produce a lambda, right? So what if Alice has lambda 1, Bob has lambda 2, and Charlie has lambda 3? So what's the overall lambda is going to be the sum or product, whatever. It's just basically it's a joint function. I think in reality, usually you can think about it as like you multiply them all together. So what does that mean? So if you have the final lambda, in order to have the final lambda, you have to have 3 of the 3, right? Lambda 1, lambda 2, lambda 3, right? Because if you're missing any one of them, you are not going to derive the final one. So what does that mean? So that translates the trust assumption to be, hey, you have to trust one single party, so-called trust third party to perform the setup. Now you are translating the assumption to be, if any one of these, multi-parties that are honest and they throw away their own lambda, the whole thing is going to be safe, right? Because it's going to be a product of all of this. And if you're missing any one of the lambdas, you're not going to derive the final lambda. Is this sensible?
Yep, that makes sense. Yeah, you need all
okay.
the keys put together for it to be a valid key.
Yes. So in this way, there's a little bit from threshold, keys. You can almost think of, because threshold you may have a way, you may not have all the share, split keys, but if you have let's say a threshold of them, you can still reconstruct the final key. But here, this is not the case. You need all of them to have this. So that's what one way for people have been trying to do. So the idea is, if you don't trust one single party, why not just share the trust among, let's say, n parties? And if this n party, any one of them is honest and throws away the lambda, then you're going to be good, right? So that's what people have been trying. The primary example, they call it the Zcash. They have a setup ceremony. It's kind of like esoteric. So basically, they pretty much went in the wild. They produce some, the computation. They get the lambda. Then they either hammer the laptop, break apart the hard disk, and they do this everything. There's no network. They record the whole thing. They have a huge ceremony in the wild. So that's one way to do it. And there's even some people, they want to get some randomness, and they even fly a helicopter to Chernobyl, the defunct nuclear reactor. So that a lot of people are doing a lot of crazy stuff just to make sure this is actually random, because if this is not, the whole system breaks down, right? Especially for Zcash. If you somehow get access to the toxic waste, you can literally create money out of thin air. So you don't want to have that to happen. And also, for all the, very famous ZK enabled applications like Zcash or Tornado Cash, now everybody heard about it because it's been sanctioned. So that's also trust setup ceremony, Aztec, that's most of the projects that have been using this way to MPC to have this set up to reduce the trust assumption. That's what actually have been happening. So that's just one way to do it. Basically, use MPC to reduce the trust assumption. And so, for example, we talk about in the previous two sessions, we talked about two type of tools to all tool chains to do ZK snarks. But there's a few ways you can do this trust setup, and some of them are better, and some of them have their own trade-off. So I just talk about one type, right? So the MPC. So here's the trick. So even you can produce, if we go back, right? Let's say this slice, because if you remember here, this is the output you want to have, the pair of keys, and it actually has two variables here, right? One is the lambda, which is randomness. The other way is also the function you want to prove. Also a lot of time in the 09 terminology called a circuit, because usually you represent the function you want to compute in terms of a circuit, arithmetic circuit or Boolean circuits. So it's a circuit. So even you have this trust setup using MPC, but here's the issue. Anytime you have a different function, you're going to do this again, right? So, I mean, one time is probably okay, right? You go through all this process, involve a lot of people, do a lot of, esoteric things. And, if you just do the MPC naively, you don't change anything else. Okay, go ahead.
Yeah, on the last slide, I just thought of a question. If you could back up. I'm sorry, one more.
Okay, yeah.
So how's that function being computed? Like, and who's doing it? Without knowing the inputs.
Yeah, I think a good analogy, I think this is a little bit math heavy. So analogy would be like, let's say a threshold signature, right? So that's no dealer. Pretty much dealerless, you can think of. That's no central party. You can do this distributedly. So basically, let's say, for example, right? Let's say you want to compare two numbers. You want to say, let's say, instead of a Yas millionaire, right? The two millionaires now, instead of say, hey, who's richer? They can say, hey, do we have the same birthday, right? But they don't want to tell each other exactly what the birthday is. So they can, I mean, the simplest example, right? You can think of the birthday as a private key. So they can just derive the, times G, the generator on the elliptic curve. They can give the public key, pretty much like a similar, right? So you can say, hey, if these two public keys are the same, then we can be sure, right? Our birthday is the same. I mean, assume that's some assumption. So basically there are ways to existing cryptography techniques enables you to do this, or even for the threshold signature, right? So nobody in the middle, right? So you can say, hey, I construct my pair, my shares, I sign it, and you sign it, and also Charlie signs it, and eventually we send this message between ourselves, we can check, and then eventually we are going to combine them, right? So similar here. There are many, it's like another whole category, it's probably bigger than zero knowledge. So it's MPC, there are many existing algorithms to perform this. So in a zero knowledge setup, they have this so-called, the most famous one. I think it's a device by Zcash people or some other people. It's basically called, powers of tau. So powers of tau, this is the algorithm they use. So if you look at the paper, basically, pretty much the toxic waste is in terms of this, they use this Greek letter tau. So if you use this algorithm we introduced before, Stark, so that's a secret, and the secret is tau and different powers, tau to the power 1, tau to the power 2, and to, let's say, tau to the power 1000. So this is a MPC using called powers of tau. So if you want to know more, I think I'm going to put a few links in the show notes. But now for now, you can pretty much regard it as like a black box. There's people is already addressed in the MPC world. Go ahead. Okay.
The next slide has some links. Would you be posting that in the Slack group?
Yeah, Slack I'll also put it in the show notes.
Okay, perfect.
Okay. Yeah, this is just pretty much you can think about all these people that are performing the powers of tau ceremony. So they have an existing MPC particle they devise specifically for the trust setup. So basically, I just talked about, I think here I'm going to talk about more. So basically you have, let's say, instead of one party, you have 10 parties. So each one that you can add some more your own randomness into it without disclosing it. So you can just iteratively produce this setup until you are satisfied, right? So usually called the powers of tau ceremony. So that's the one we call the updatable. So I just talk about the one type of, the simplest and naive approach to do setup, right? The drawback is even you do MPC, the drawback, every time you have a new function, basically you have new problem to prove. You have to perform the whole thing again, right? You don't problem. So in reality, what does that mean? So you have application 09 enable application 1, you have to produce a trust setup, the setup ceremony. And then you have, if you upgrade it, let's say you change it, there's a bug, you want to fix it, you have to do it again, right? Or somebody else has another app, you have to do the whole thing again. Right? It's so-called per circuit or per function trust setup. Trust setup thing is this like an offline thing. A lot of people have been involved, and it's quite, it's not just something you enjoy will be doing. So that's why people have come out with a new type of algorithm. So basically, there are some other like zero-knowledge protocols that can enable us to do so-called universal setup. Well, what does that mean? So basically, it means it's a circuit agnostic, right? For example, you have F1, F2, F3. They're proving different functions. For example, F1 could be Zcash. F2 could be like a tornado type cache type thing, a zip. Type 3 could be, let's say, dark forest, right? Some kind of ZK game. So if they perform a trust setup that's universal, what does that mean? That means you can use the trust setup, the parameters for all. You can use a pair of keys for all kinds of applications. It doesn't have to be bound to a specific proof. So that's much better, right, than per circuit, because you can say, let's just perform once, right? This trust setup, because it's very complex and involve a lot of people. So I can just produce it once, and then every application can just reuse this trust setup. Right? That's much better than every time you have to do a new one if you have a new circuit. Make sense? And then there's a related concept called upgradable. Basically, that's what the powers of tau. Let's say now you have a trust setup and it's not static. You can actually iterate on top of it, because, for example, right, simple example, somebody produced, let's say Zcash people, they perform a trust setup that's universal. But hey, I'm just paranoid. I don't trust these people. I don't trust anybody. I want to add my own lambda randomness into it, right? So you can add one iteration, and then you update the so-called pair of, prover key and verification key. You get a new pair of keys, right? You trust this pair of keys because you trust yourself, you can throw away the randomness, right? So that's what the powers of tau ceremony is coming. So basically, they have existing participants, at least A, B, C, D. So if you want to add your own randomness, you can add into it. And then you can do this anytime. So that's called a perpetual, powers of tau, perpetual, because you can keep adding randomness into it. It doesn't have to stop. So that's another type of trust setup. So the last one, they call it transparent. So what that means, pretty much there's no trust setup. So that's introduce us to the next topic. So I talk about usually two ways to get around the trust setup issue. One is to, reduce the trust using MPC, right? So 1, 2, 3, you can think about there's different approaches to do different types of trust setup. But of course, the best way would be you don't have to, you can completely remove this trust setup, right? You trust nobody. Then that's much better, right? Because if you don't have to trust anybody, everything that can be done in the wild. Everybody can see every process. There's no secret. So that's why it's called transparent. Basically means you don't need the trust setup at all. There are some new ways you can produce. You can run the zero knowledge, but you don't have to. There's no trust setup phase at all. So I'm going to show you a few examples, which I think I put it before. Can you see my browser? Okay, that's good.
Yeah.
So I think I shared this earlier before. So basically, I talk about ZK snarks, right? So there are different ways. I think for ZK snarks, I think here there's a link. Basically, I just talk about in the current slide, I talk about, you'd have different. So usually they are also called the pair of keys. They are called a reference string. Reference string because it's referenced by both the prover and the verifier. It's like a public knowledge, almost like a public key. But in this case, it's a pair of keys, the prover key and the verification key, the reference string. So it's called common reference string. So you can see here, some of them is circuit specific. So for snark, there are different algorithms, right? There's an umbrella consisting of many different algorithms. So the one we implemented so far is called Gross16. So basically, it's this professor named Gross. He published in 2016. So usually people denote it as Gross16. So it's per circuit. So if you are using our tools right now, Circum or Socrates, for every circuit, you have to perform this trust setup. So I just also talk about some of universal, basically some of the newer zero knowledge stack. For example, Sonic, Marlin, Plum. So it's universal, meaning you only have to do it once, and then every app can reuse the trust setup. They can use the pair of keys. They don't have to redo their own thing. So that's universal. That's also universal. Some of them is also updatable, meaning you can keep doing it. If you can keep adding random into it. So that's the 1, 2, and 3. We talk about the type 4 is the one we call transparent. Basically, this means you don't need trust setup. You completely remove trust setup. Okay. So, for example, this is the ZK snark here. We mostly talk about ZK snark, right? So the other type of zero knowledge protocols that's completely remove this trust setup. Okay. So for example, you may probably heard about bulletproof, right? So if you use some kind of like a Monero, so this is a core technology called a bulletproof. Also, you have some other blockchains also use this for so-called confidential transactions, basically to hide the amount of value you are transferring. So trust setup is not an issue here because there's no trust setup at all. Or you may probably heard about ZK Stark. You may also hear about ZK Stark. The T means transparent, meaning whenever you hear the name transparent in ZK, that pretty much means you don't need a trust setup. But here's the thing, right? And then you say, hey, if trust setup is an issue and this seems like a newer zero knowledge protocol, just completely remove it. Why not? Why are people still using snark at all? Let's say Gross16, right? But here's a trick, right? And it's a trade-off. Right? For example, now you get rid of trust setup, right? You may suffer some other, in some other criteria, you may suffer, right? For example, bulletproof, right? So, for snark, the verify is very fast. It can be milliseconds, or we can even put it in script, right? That's what we did, because it's pretty much constant size. It doesn't matter how. That's amazing thing, right? It doesn't matter how complex your computation is, basically your circuit is, doesn't matter. The circuit is only 1 gate or 1 billion gates, it doesn't matter. It's a constant verification time versus bulletproof. Now you get rid of trust setup, but you're going to have almost a linear verification time. Basically means the bigger the circuit, the longer, the more complex, the longer it's going to take to verify. So it's a kind of trade-off. You know, it's all you have to decide what kind of proof system you want to. Proof system, you can think about all the 3 algorithms: setup, proof, and verify. So this is what a ZK protocol contains. So depending on what your use case is, you know, you may say, hey, I just want to minimize my verification time because I'm going to put it on blockchain, let's say Bitcoin, right? So that's why I think the #1 use case for us is we want to minimize the verification time. So even though we need the trust setup, but we're going to do it, even it's kind of like a pain in the ass, but we're still going to do it because it's going to save us a lot of transaction fees, right? Or if some people say, hey, I don't want to trust anybody, I'm going to choose, you know, maybe Stark, which give me some, you know, a big proof size. It can be 100 kilobytes instead of like, let's say, less than 300 bytes. So I'm going to choose this because, you know, I'm like some other alternative blockchain, right? I cannot afford to put 100 kilobytes on my blockchain. So I don't want to do that. So I'm going to choose Stack. But let's say I'm on Bitcoin and have some application. I don't want to rely on some trusted party. I can choose to run on Stack, right? Even though it's 100 kilobytes, but it's still economic on Bitcoin SV, right? So it's all different trade-offs. Any question here?
This is semi-related. So miners in BSV right now are charging based on script size. If they ever charge per operation, like are the Bitcoin script operations being done here like much more expensive for miners to validate?
Yes. So right now, yeah, very good question. Basically, you know, the miner is just charged by the length of the script, right? The size of the transaction, pretty much the size of the script, because that's like a heuristic, right? So usually, in general, it's highly correlated. That the longer the script, the more resources it's going to take to verify, to write, right? So it's just approximation, and because now they're not huge volume, so it doesn't matter much. It's not, you know, if you do like an op-add and you do another op modular, it's probably going to the modular, depending on the argument, but you could imagine, right? The modulars operation is probably more expensive than just add. Or if you're doing even crazier thing, you are doing op check sig, right? You know, even one is just 1 byte, it was the same with op-add, but it's going to be like 1 million, almost like 1 million times more expensive, right? Because check sig, you pretty much run the ECDSA, the whole algorithm, which is non-trivial. So right now, I think people just regard that every opcode costs the same amount of resources to validate. So that's why they just charge on based on the size of the script. But I think if more and more script, pretty much just smart contract transactions going to show up on the mainnet, I think definitely the miner is going to change the fee structure based on, if I'm a miner, I'm a little bit of a, you know, I want to get ahead of the curve, I'm not going to charge it just based on the length, right? Because that's not a real reflection of the actual cost. I think it's going to evolve, and more as you have a bigger volume and then more complex script coming on, they're going to charge approaching the cost of actually what's the actual cost of running script. But right now, people are not doing that yet. Okay, any other comments? Any questions? Okay. Yeah, if not, I mean, that's all I have to cover today about the trust setup. So any concluding thing?
I saw in the last episode, I call it episode, the last class.
Okay, that's good.
I saw that there is a website that actually went, is there a class that goes through exactly what we just went through right now, so I could like get more into detail with it?
Are you talking about kind of like a
The
a tutorial?
website, the script, what I think it's from Script, Script,
Okay.
yeah, there is a website that I saw that you guys had pointed to last class. That's the one, learn.script, that's the one. Yeah,
Yeah,
so
yeah.
is this a particular lesson that we just learned today already included in this year?
No, this is the outside. Basically here, this basically is a pretty hands-on tutorial you can walk through to build a so-called ZK battleship game, and then you can integrate with some kind of like a front end so you can play it. And
Okay,
we're not covering the trust setup. Trust setup is something like outside of this course because this course we just want to walk through the process. But if you want to actually deploy to production to deal with people's real money, you have to go through the trust setup ceremony. But right now here, because we just want for people to how to do it, so you don't have to walk through because trust setup. Let me actually now is a good time to to walk through a little bit of just give you a sense how that looks like. For example, we have two tool sets, right? One is called Socrates. The other one is here. It's called Circle plus Snark.js. So this is one tool for you to produce the ZK Snark. So so they have a trust setup. They call it the powers of Tau. I just talked about it before. So you can produce this. They have a tool. Basically, they already integrate how do you do the ceremony into the tool set. They call it Snark.js. You can compute. You see here, you have to you can perform trust setup multi-party ceremony, including the universal powers of Tau ceremony. So I talk about it here. The universal means people already run this before. So if you want to search just setup, you can even download. This is already the people already produced. Let's say Vitalik, whatnot, just hundreds or tens of people, even sometimes hundreds of people have participated in this trust setup, and they have produced this file. You can think of this almost like a transcript of everything here there. You can verify everything is being done correctly so far. So this is the trust setup, and then because it's updatable, right? So it's called powers of Tau. You can also add your own random list. So basically, this is some public information, gigantic file, basically gigabytes. You can download, and then if you don't want, you can use this because it's universal. But if you're paranoid, you want to, hey, I don't want to trust all this public ceremony. I want to also add my own pretty much random list. You can also apply your own random list. You can put any number, your hash, your birthday, or whatnot. Or you go, I don't know, you measure the hurricane speed at a certain time in certain place in Florida. You can add this random list here. So basically you can have people already done this power of Tau universal setup. And if you want to have a new application, you want to produce your own setup, you can add your own randomness on top of it. So the idea is if anyone of all these participants, including yourself, is honest, you can trust this setup, okay? And this tool already give you all the command lines, the CLI command lines. You can produce this powers of Tau. You see here? So this is the powers of Tau, the file. So this is pretty much you can think of the whole ceremony. They put in this file. You can download this file and apply your own. You can either directly use it or you can also add your own random list. This is what actual setup looks in the wild, how you actually use it. But since for this example, I just because this is quite complicated and it's only needed if you just run some demo, you don't need this. Right? So that's why I didn't put it here. But that's if you really want to launch some application, ZK in production, dealing with real assets, you have to go through this whole process of, the whole ceremony. And you can do it with this tool called Snack.js.
Okay. I think I'm gonna start with the basic lessons first.
Yes,
then,
that's a good start. Yes.
Yeah, I'm gonna do that because I feel like my understanding is very basic right now. So I'm just gonna have to start, baby steps, and then I'll get to that after.
Yes, I think that's more like, that's advanced topic, I would say, because, if you want just to build some kind of like a games or some kind of simple applications based on zero knowledge, you don't need to worry about that because you're not going to put a lot of money into it. But if there's real money at stake, you have to go through this very, very much intensive and laborious process to make sure the setup is trusted. Or if you're even fancier, you can even say, hey, I don't want to use this, even at the cost of bigger script or transaction. I want to use some other neural proof system. You can also do that. But I think that's one thing. I think most majority of people, while they have been doing this MPC-based trust setup, so they're not using. I think some cases they're using other neural proof system, but they also have their own drawbacks. So it's your choice.
I forgot to ask. In the reading, it said the Zcash blockchain had an update based on some vulnerability.
Yes.
Can you talk to that a little bit?
So Zcash basically, when they first launched in the first version, they performed this big, gigantic, famous trusted ceremony, as I talked about, right? They went to some desert. They record the whole thing. They cut every network access. Then they perform all this thing on the laptop, and then they crash use a hammer to just crash all the laptop. They break up the hard drives. It's very, dramatic. But then later on, turns out it's not the trust setup that's compromised, but basically the algorithm they use is actually has some drawbacks. Basically, they have some vulnerability, and people write some papers. They discover that it turns out you can be attacked. So the attack is such, even you don't have any, you can mint Zcash out of thin air. So then later on they have to upgrade the protocol. Basically, have a breaking change to upgrade it to patch the vulnerability. But here's the crazy thing: nobody knows whether anybody has exploited the vulnerability today, and nobody can check. That's the crazy part, right? But that's also, you can see that's Bitcoin model is good because it's transparent. Even there's a bug, I think that's early days. The Satoshi had the bug that's causing overflow, and people can create money out of thin air. But the good thing is people can check it, right? But the Zcash, because everything is pretty much encrypted, you don't know. So to this day, nobody knows. They upgrade it, they patch it, but we don't know. There's no way for sure. So keep going.
I'm sure someone tested the theory.
Say it again.
I'm sure someone did it. That's what I put my money on.
Oh, okay. Yeah, that's
I'm
a
with
hearsay,
Brandon
right?
on that one.
Yeah, you don't know, right? So if I'm like the first one to detect this, I just do it because I'm never going to get caught, right? Everything is hidden.
That's the thing with a lot of this. It's like, how many
Yes.
people in the world have the ability to audit this, like, realistically?
I can probably count with my own one hand, if not two.
Right. So it's like any application you build. I mean, if you're a developer and you're not one of these 10 people, it's like, how confident can you be? Because you're not auditing yourself. Like you don't have the ability.
Mm-hmm. Yes, I think that's all like pretty much all other software system there is pretty much just to see how many how usually it's like a battlefield testing, right? So if it's been running for a long time and has been, let's say, a lot of stake in it, like let's say Bitcoin, right? I wouldn't say I cannot prove it's bug free, right? But it's been running for like 13 years, and if somebody already knows some way to hack it, they would have already done it, right? So the fact that it's been running for so long and nobody has hacked it, it pretty much
Right.
give me a very confident. Same over here. That's why in the 0.9, I think I talk about for example, right here, this is the one that's the earliest, and some people come up with newer proof systems, but in the wild you still see this one is like a dominant, because even though some people say, hey, I don't have trust setup or this drawback, but since this is newer, so it's just more risky, right? Because this, let's say Snark has been using for Zcash, Tornado Cash, or a bunch of other stuff, right? Has been pretty much like tested much longer than the newer ones. So that's always a trade-off, right? So there may be some newer ones that's supposed to be better, but you probably want to have it. It's like any other thing in cryptography. The longer that it's been around, let's say RSA or ECDSA, right? I think usually people trust those because it's been around for many decades, and no serious vulnerability has been detected so far. So that's another reason I think I kind of like bullish on the zero-knowledge games instead of like a financial kind of apps, right? Let's say Zcash or Tornado Cash, because if it's a game, if there's some vulnerability being exploited, that's not the end of the world. You see what I mean? Maybe I have some, I don't know, I have some Pokemon, I have some crypto kitties, and somebody steal it. It's not end of the world. But if I'm putting all the savings or something translated to some kind of like a private, so-called private, or even anonymity, focus on cryptocurrency, and then there's a bug, somebody exploited, either in the trust setup or in the algorithm itself, and then the whole thing breaks down. That's not something I can tolerate. But if it's a game, it's not end of the day. So yes, that's another criteria. Just how long it's been around, and what kind of value people have been staked into this, being supported by each algorithm. That's also another criteria. When you choose which one to build on.
I mean, there could be a vulnerability in the new Zcash algorithm, but you didn't have a good actor, come out and say it. Like he'd just be using it now theoretically, and there'd be no way to find out unless you audit it yourself.
And so that's a crazy one. Even you are, so I think today we are talking about trust setup. That's just one attack surface, right? So if you compromise the trust setup, everything goes down, because you pretty much have you enter God mode, right? You can produce anything you want. But that's just one big surface, attack surface. Then it's just one type, and you have even in the prover side or verifier side, you can also have attacks vectors, right? So that's just one way to attack the system, one known way, right? And I'm not saying anything about, and also it's like software system, end of the day, even the algorithm is good, you don't know, right? You also have to audit the implementation. Even the algorithm is good, right? So ECDSA, if your implementation is not good, for example, the Sony, right? PlayStation has been hacked because they are reusing when they generate the nonce, it's not random. So if you reuse the nonce when you are signing, people can recover your private key. So that's what actually happened. So in reality, yes, for zero-knowledge type of applications, if you that's real stake and dealing with people's huge amount of money, you have to go through the formal verification, audit. That's an opportunity, right? So if you know enough, you become a ZK knowledge expert, you can be an auditor yourself. So I could imagine it's similar to smart contract audit, but it's a little bit different. Right? The smart contract, you probably right, they have their own type of vulnerability, re-entrances, or whatnot. But in zero knowledge, there's another type, completely different types of securities. You have to think. Yeah, that's another reason, right? We learn about this, so we study it together. At least we know we can rule out some of the existing known vulnerabilities when we are developing our own ZK apps. And also we can develop tools that can help developers, to alleviate this kind of problem. Okay. Anything else? Anything? If not, we can just call it a day, and we can see you next.
Thanks for
Hopefully, see
doing
you next
this.
week. No problem, man. Thanks again. Thanks for making it. Okay. Hope to see all you next week. Okay. All right. Thanks, guys. Enjoy the rest of the day, and hopefully see you next time. Okay. Bye-bye.
Right.
Bye-bye.